Dear students, now we discuss some important analytical results. Existence and uniqueness. We consider retarded differential equation. Consider the retarded difference equation. Okay, delay equations are also called as differential difference equations. Okay. So this is general equation which we discussed yesterday. X dot of t equal to ax of t plus b x of t minus r plus f of t where a, b and r positive are constants and f from r to r is continuous. So we consider this equation along with initial data, namely x of t equal to phi of t for t in the interval minus r to 0. We call this equation as 1 and this initial data as 2. And we now state existence and uniqueness result. Theorem. If phi is given continuous function on the interval minus r0, then there is a unique function x of phi f. X of phi f means this is solution x which depends on phi and f. Okay, so this thing means dependence on phi and f defined on minus r to infinity that coincides with phi on minus r interval minus r 0 and satisfies equation 1. That means there exists unique solution to this problem 1 and 2. Okay. This x coincides with phi and satisfies equation 1 means this function x is unique solution of this initial value problem 1, 2. Let us prove this result. Proof is not difficult. In this proof, we use method of steps. Okay. So first we convert given problem to integral equation using variation of constants formula, and then method of steps provide solution. Okay, and this solution will be unique. Consider the equation 1. Consider the initial value problem. In short, we write IVP 1, 2. Variation of constants formula implies x of t equal to e raised to at into phi of 0 plus integral from 0 to t e raised to a t minus s into b x of s minus r plus f of s ds. Okay, this we discussed yesterday. We call this as 3, and this is for t greater than 0. Of course, it is true for x equal to 0 also, t equal to 0 also. At t equal to 0, we have x of 0 equal to phi of 0. The method of steps gives the solution x depending on phi and f, which is function of t, equal to xi of t for t in the interval I minus 1 into r to ir, I equal to 0, 1, 2, and so on. Okay, this we have seen yesterday. Use the solution to IVP 1, 2 such that x0 of t, here t belongs to minus r to 0. Okay, if we put I equal to 0, then interval is minus r to 0. In this interval, solution is phi of t. Okay, note that this x naught is unique because phi is given function. Since phi is given, X naught is unique. Similarly, x1 of t equal to e raised to at phi of 0 plus integral from 0 to t e raised to a t minus s into b. Now we write x0 of s minus r. X0 is known. Instead of x, we substitute x0 plus f of s ds. Here t belongs to closed interval 0 r. Okay. Again, x naught is unique. F is given function. All others are constants a, b, etc. So x1 is unique. Okay. Note that this x1 is uniquely determined. We can continue this procedure and find unique solution x of phi f of t, and this proves the result. Continuing this process, we obtain unique solution x of phi f of t on minus r to infinity to IVP 1. This proves the result. Now we see some properties of this solution. Result is, if x of phi f is the unique solution of IVP 1, 2, then x of phi f of t has a continuous first derivative for all t greater than 0. That means this solution is continuously differentiable function for t greater than 0. We also call this class as C1 functions. That is, this x is C1 function on 0 infinity. x of phi f has continuous derivative at t equal to 0 if and only if phi of theta has a derivative theta is dummy variable for phi. Okay, that means phi is differentiable at 0 with phi dot of 0 equal to a into phi of 0 plus b into phi of minus r plus f of 0. Okay, we call this as 3. Okay, so this solution is C1 for t greater than 0. It is C1 at t equal to 0 if and only if the initial function phi is differentiable at 0 and it satisfies given differential equation. Okay, what is meant by phi dot of 0 equal to a into phi of 0 plus b into phi of minus r plus f of 0? This means phi satisfies equation 1. Okay, we can see equation, this is equation 1. So if phi satisfies this equation at t equal to 0, then phi dot of 0 is a into phi of 0 plus b into phi of minus r plus f of 0. Okay, this should be 4. Let us see the proof. Consider equation 1. Now see the right hand side. We have seen that this function f is continuous. Okay, this x is solution. Okay, so it should be continuous function. Okay, so a into x of t plus b into x of t minus r plus f of t. That means this right hand side is continuous for t greater than 0. This means left hand side, that is x dot of t, is also continuous for t greater than 0. That means x is C1 function for t greater than 0. Since the right hand side of equation 1 is continuous, for t greater than 0, x dot of t is also continuous for t greater than 0. That means this x is nothing but solution. So whether we write x or x of 5, that doesn't matter. Okay, that is x of 5 is C1 for t greater than 0. Okay, so this proves first part. Now second part. We assume that this solution x has continuous x is c1 at t equal to 0. Now assume that this x of f is c1 at t equal to 0. That means this x of f has continuous derivative at t equal to 0. Then this solution coincides with phi, okay, for t in the interval minus r to 0. So phi is also c1 at t equal to 0. Okay, that means we can find derivative of phi at t equal to 0. Then since x coincides with phi on minus r0, phi is differentiable at 0. And since this is solution, phi dot of 0 is same as x dot of 0. But x dot of 0 is nothing but ax of 0 plus bx of minus r plus f of 0. Now x of 0 is same as phi of 0. X of minus r is same as phi of minus r and plus f of 0. Okay, so phi dot of 0 is a phi of 0 plus b phi of minus r plus f of 0. Okay. Conversely, if we assume that phi dot of 0 is a phi of 0 plus b phi of minus r plus f of 0, then phi dot of 0 must be same as x dot of 0. Further, we are assuming phi is differentiable at 0. So x derivative of x is continuous at 0. Okay, because in that case we will take a right hand side derivative. Okay, so derivative is right hand side derivative and it will match with phi dot of 0. Okay, so limit as t tends to 0, x dot of t is phi dot of 0. Okay, so converse is similar, or we can say that converse is obvious. This proves result. The initial data, that is function phi, is given to be continuous. However, we don't know whether it is differentiable or continuously differentiable. If this function phi is continuously differentiable on some intervals, it may be very small, say minus epsilon to 0, then we can extend our solution to left hand side of minus r. Okay, let us see. So this is, say, minus r, this is 0. If our function phi is continuously differentiable for some interval, say minus epsilon to 0, then we can extend our solution of this IVP 1, 2 to left hand side of minus r. Okay, so this solution exists on the interval minus r infinity if phi is C1 on some interval, say minus epsilon to 0, then this solution can be extended to left hand side of minus r. Okay, so it exists on minus r minus epsilon to infinity. Then phi of x of phi f exists on larger interval minus r minus epsilon to infinity. Okay, so we can extend it further to left hand side if we put some more conditions on phi, like phi is C2 twice continuously differentiable, as well as function f is differentiable. Okay, at present it is continuous. If function is f is differentiable, phi is C2, then we can extend it further. Okay, and so on. So we see this result. If b is not equal to 0, then the solution x phi f can be extended as a solution of IVP 1, 2 on minus r minus epsilon to infinity, where this epsilon is smaller than r. It is positive but smaller than or equal to r. If and only this is possible, if and only phi is C1 on the interval minus epsilon 0, closed interval minus epsilon 0, and one more condition is usual, that is derivative of phi at 0. That means phi satisfies this problem at t equal to 0. Okay, phi dot of 0 equal to a phi of 0 plus b phi of minus r plus f of 0. This condition should be there. Okay, if we want to extend it further, then we may need more conditions, like phi double dot of 0 uh, is satisfying certain conditions. Okay, like a into phi dot of 0 plus b into phi dot of minus r plus f dot of 0. Okay, and phi dot of 0 equal to a phi of 0 plus b phi of minus r plus f of 0. Okay, let us see the proof. So we assume that phi is C1 on this interval, and this is satisfied. Okay, so it is number 4. Okay, and 4 is satisfied. We have So what we do, we consider equation 1. So we rearrange equation 1. Okay, so what we do, we uh, write this equation 1 as x of t minus r equal to 1 upon b into x dot of t minus ax of t minus f of t. Okay, we can divide by b because we are assuming b non-zero. Okay, so dividing by b and rearranging, we can write equation 1 as x of t minus r equal to 1 upon b into x dot of t minus ax of t minus f of t. Rearranging 1. Okay. Now, right hand side of this equation is known explicitly for t in minus epsilon to 0 because x is solution. X is nothing but x of 5. It is defined on minus r to infinity. Okay, so right hand side is known explicitly for t in the interval minus epsilon to 0. This is our assumption. Okay, we assume that this phi is continuously differentiable, so no any harm, we can differentiate x and so on. Okay, so this is known explicitly for t in minus epsilon to 0. So what this means, left hand side also known explicitly for t in minus epsilon 0, but left hand side is x of t minus r. If we put s equal to t minus r, then t belongs to minus epsilon 0 implies s belongs to minus r minus epsilon to minus r. Okay. Therefore, LHS, left hand side, x of s is known explicitly for s belongs to minus r minus epsilon to minus r. Okay, so this proves one part. That means we can extend solution x to left hand side. Okay, so now solution is defined on this interval also, minus r minus epsilon to minus r. So actually solution is defined from minus r minus epsilon to infinity. Okay, that is the solution x of phi f is defined on minus r minus epsilon to infinity. That means it can be extended to left hand side of minus r. Now converse part. If we assume that x can be extended as solution of IVP 1 to on minus r minus epsilon to infinity, then that means x is defined on this interval also. So further phi should be C1 on this interval minus epsilon to 0, and it should satisfy this equation. Phi dot of 0 should be same as this. Okay, so converse is obvious. Converse is obvious. Thank you.